Hello everyone, welcome back. This is our 6th video in our series, and here I will be talking about what happens when we turn sources off. There are actually many cases where turning sources off is necessary. For example, we might want to understand a circuit's behavior if one of its particular sources is being turned off and everything else remains on. That way, for example, we can see what the impact of every single individual source on the circuit might be. So how do we do that? First of all, let me remind you that this is the taxonomy that we have been working on. So we're now focusing on the 6th and last part here of turning sources off. So there are different ideas, different methodologies for turning off voltage sources and current sources. So this is an example of a circuit that basically has 3 voltage sources, V1, V2, and V3. Even though I'm giving you this example with independent voltage sources, the same thing is really true for the dependent sources. So how do I turn off a voltage source? Turning off a voltage source essentially means making sure that the voltage across it is 0. So for example, turning off V3 would mean that I need to ensure that V3 must be equal to 0. The easiest way to do this is to essentially replace this voltage source with a short circuit, literally meaning a wire that connects its terminals. This wire is called a short circuit. Similarly, if I wanted to turn off V2, I would have to introduce a short circuit across its terminals. So the minute I put a cross circuit there, or to be more precise, the minute I remove V2 from my circuit and replace it with a short circuit, I will ensure that V2 is 0 volts. So turning off a voltage source means for us replace it with a short circuit all the time. So it's really a simple rule to remember, and of course it's a very intuitive rule. Why does replacing a voltage source with a short circuit make sense? Because we do know that in a short circuit the voltage drop is 0. By definition, the voltage at this point is equal to the voltage at this point, therefore the voltage drop V3 is 0. Similarly, the voltage at this point is exactly the same as the voltage at this point. They're connected by wire, therefore the voltage drop is 0. Of course, exactly the same thing would happen in V1 or in any other situation where you have to turn off a voltage source. Just replace it with a short. In exactly the same way, we can think about the case of a current source. This is basically the same circuit, but now I have 3 independent current sources. So how do I turn off a current source? So let's think again. If I want to make sure, for example, that I3 is 0, I want to turn off that source. Essentially, I need to ensure that there is absolutely no current that flows from this point to this point. So if I want to ensure that there is 0 current, it basically means I have to replace this guy with an open circuit. An open circuit is basically a break. There is just literally nothing there. The source has been removed and has been replaced by nothing. The circuit has a break. It's called an open circuit, and as we already well know, there is no current flowing in an open circuit. More precisely, there is no DC current flowing in an open circuit. So far we're talking about DC, so this is what I'm going to focus on. Similarly, I2 will be turned off if it's replaced by an open. So if I remove it from my schematic and I basically literally replace it with nothing. So the rule that you need to remember is that turning off a current source is implemented by replacing it with an open circuit. And this is exactly what we do all the time to turn off current sources. So remember, turning off voltage source, replace them with a short. Turning off a current source, replace it with an open. Now, open circuits and short circuits do not only occur in circuits whenever we're turning off sources. So I would like to use this opportunity here to say a few things, some of them from a very practical perspective about open and short circuits. So first of all, let me show you a couple of schematics here where you can clearly see an open circuit implemented literally as a break. So it's just an open. There is just nothing there. And once again, DC current cannot flow through an open. Now, are open circuits good or bad? They're neither. Sometimes they occur intentionally. For example, sometimes we do in real life remove sources intentionally, and therefore there is an open circuit intentionally. Sometimes they occur by an accident. For example, maybe there was actually something here. Maybe, for example, there was a fuse. What is a fuse? It's actually a device that allows current to flow as long as this current is below a threshold. If the current actually goes above a threshold, perhaps due to an accident or maybe due to lightning, that fuse will basically burn, resulting in an open circuit. Essentially, that happens because the fuse is burning and protecting the rest of your circuit from the damage. So open circuits sometimes in real life do occur because of fuses, or because something actually got burned or something got damaged that may have happened intentionally in the case of a fuse, or unintentionally if there was an accident and there was perhaps no fuse. Similarly, short circuits occur intentionally or unintentionally. Perhaps, for example, if you look at the circuit here to my left, one might want to simply bypass a device. So you might say, okay, somehow I don't need this device A anymore. I'd like to make sure there is no current flowing through that. Well, if there is no current flowing through that, all you have to do is introduce this short circuit across the device. Now, as the current is flowing outside of the source here, it's going to come to this node. It's going to think, do I go up or do I go to the right? Well, if it goes up, it will face a short, meaning no resistance. It will essentially be a free flow. And this is the path, as we call it, of least resistance. So the current will enjoy this path far more than going through the device A, where actually some resistance will be faced. And so whenever you essentially introduce a short circuit, you allow a current to bypass the device, and that way you can perhaps reconfigure your circuit, allowing it to perform a different function. On the other hand, you should be very careful with short circuits because unlike open circuits, they're far more dangerous. For example, if you want to introduce this short circuit here, just because you may be thinking, okay, I now want to bypass my entire circuit, how about I just introduce this blue circuit here to just bypass everything? Well, you have to be very, very careful because now you're basically forcing the current that flows from this independent voltage source to essentially go through a path of zero resistance. We'll discuss resistance in more detail later on, but I'm sure that you all have an intuitive understanding of that. Essentially, that means that this current I could be simply too high. And if this current I now is too high, because you're forcing this current to go through a path of practically zero resistance, you may be up for some very, very unpleasant surprises. Something may get burned, cause fire, or even worse, cause injury or death. So you need to be very, very careful where intentionally you're introducing short circuits to bypass devices. You may actually create a dangerous condition. On the other hand, this short circuit here may not be intentionally introduced. Perhaps there was already an accident. Maybe there was some lightning. Maybe some fuse got burned in the wrong way, and therefore a short was created. So this was the last part of this video, and I hope you have a better understanding of how we turn sources off, and in general, when do we encounter open and short circuits in real life. So thanks a lot. We'll see you next time.